Welcome! In today's session, we'll explore LeetCode problem number 393, UTF-8 validation. This problem challenges us to verify if a given list of integers represents a valid UTF-8 encoding. It's a great opportunity to sharpen your understanding of bit manipulation and validation. Let's dive in. The problem we're addressing involves UTF-8 encoding, which is a widely used variable length encoding for Unicode characters. In UTF-8, the encoding rules specify that a 1-byte character starts with a 0 followed by its 7-bit ASCII code. For characters requiring more bytes, the first n bits of the leading byte are set to 1, followed by a 0, and each subsequent byte, known as a continuation byte, begins with the bits 10. For example, a 1-byte character follows the format 0xxxx, while a 2-byte character uses 110xxxx10xxxxxx. Similarly, 3-byte characters use 1110xxxx10xxxxx10xxxxx, and 4-byte characters use 11110xxxx10xxxxx10xxxxx10xxxxx. The task requires us to determine if a given list of integers, representing transmitted bytes, conforms to these rules and is valid UTF-8 encoding. The input to the problem is an array data, where each element is an integer between 0 and 255, inclusive. Each integer represents 1 byte of the transmitted data. The output is a Boolean value, true if the data array represents a valid UTF-8 encoding, and false otherwise. For example, consider the input, 197, 130, 1. Here, 197 in binary is 11000101, which matches the starting byte format of a 2-byte character. The next byte, 130, is 1000010 in binary and fits the continuation byte pattern. Finally, 1 is 00000001, which matches the format for a 1-byte character. Since all bytes in the array conform to UTF-8 rules, the output is true. Now, let's look at a different example, 235, 140, 4. The first byte, 235, is 111101011 in binary, which matches the start of a 3-byte character. The next byte, 140, is 100011100, which is a valid continuation byte. However, the final byte, 4, is 00000100, which does not match the required continuation byte format for a 3-byte character. Because the sequence is incomplete or malformed, the output in this case is false. This demonstrates how a single invalid byte can cause the entire sequence to fail UTF-8 validation. For another example, consider 240, 162, 138, 147. Here, 240 in binary is 111100000, which correctly represents the start of a 4-byte character. The next 3 bytes, 162, 138, and 147, are 1010010, 100011010, and 100100011, respectively. All of these match the continuation byte format 10xxxxxx. Since this sequence satisfies the rules for UTF-8 encoding, the output is true. This example highlights a valid 4-byte character where all bytes align with the expected patterns. Finally, let's examine the input, 145. The byte 145 is 100100001 in binary, which does not match any valid starting byte pattern in UTF-8. For example, it doesn't start with 0 for a 1-byte character or with the appropriate 1s followed by a 0 for multi-byte characters. As a result, this single byte is invalid, and the output is false. The constraints of the problem ensure that the input array contains at least 1 byte and that all values are within the range 0, 255. Common edge cases include sequences with incomplete characters, invalid continuation bytes, or invalid leading bytes, all of which need to be carefully handled to ensure correct validation. To tackle the problem of validating whether a list of integers represents a valid UTF-8 encoding, we need to consider the rules that govern how UTF-8 characters are structured. Each character can consist of 1 to 4 bytes, and the leading bits of these bytes determine their validity. One possible approach is the brute force method, where we validate each byte individually. This involves checking the leading bits of every byte to determine if it marks the start of a character, and then verifying that any subsequent bytes in the sequence begin with the expected 10-bit pattern. This method processes each byte sequentially, which ensures an O(n) time complexity with constant space usage. However, while it's simple to implement, it can lead to verbose and repetitive code due to the manual bit-level checks required for every byte. Another method builds on the brute force approach but introduces stateful processing to improve efficiency. Here, instead of analyzing each byte independently, we maintain a state variable to track how many continuation bytes are expected after encountering a starting byte. As we iterate through the list, we update this counter based on the type of byte we encounter. For new characters, the counter is set to reflect the number of continuation bytes required. For continuation bytes, we simply decrement the counter, as their structure is straightforward to validate. This method retains the O(n) time and O(1) space complexity but avoids redundant checks, making it more concise. We can also consider a masking and lookup approach, where we define bitwise masks for valid UTF-8 structures and match each byte against these masks using predefined patterns. This method is clean and elegant but may feel less intuitive for those unfamiliar with bitwise operations, and its maintainability could be a concern in some cases. Among these approaches, the stateful processing method stands out as the best choice due to its balance of clarity and efficiency. By using a state counter to track continuation bytes, we eliminate redundant checks while keeping the logic straightforward and easy to follow. The key insight here is that once a continuation byte is identified, there's no need to revalidate its leading bits, the counter suffices to ensure correctness. While the brute force approach is simpler conceptually, it's more verbose and involves repeated validation steps. On the other hand, the masking approach, though elegant, could be harder to understand and maintain. The stateful method directly aligns with the problem requirements, ensuring that each byte is processed exactly once while maintaining a clear validation structure. This makes it an ideal and practical choice for solving the UTF-8 validation problem. To validate a UTF-8 encoding, we start by understanding its structure. A valid UTF-8 character can use between 1 and 4 bytes, each with specific patterns. For single-byte characters, the most significant bit is 0, indicating it's a simple ASCII character. However, for multi-byte characters, the first byte has a special prefix to denote the total number of bytes, such as 110 for a 2-byte character or 1110 for a 3-byte character. After the first byte, the following bytes must always start with 10. To implement this, we initialize a variable called remaining_bytes, which helps us track how many additional bytes we need to validate for a multi-byte character. With this setup, we iterate over the input array of integers, treating each integer as a byte and applying these rules step by step. When iterating through the input, the first thing to check is whether we are starting a new character. If remaining_bytes is 0, it means we are at the beginning of a new potential UTF-8 sequence. We then determine the number of bytes this character requires by inspecting the leading bits of the current byte. For example, if the leading bit is 0, it's a single-byte character. If it starts with 110, it's the beginning of a 2-byte character, and we set remaining_bytes to 1. Similarly, 1110 indicates a 3-byte character, and 11110 indicates a 4-byte character. If the byte does not match any valid starting pattern, we immediately return false, as the encoding is invalid. Now, if remaining_bytes is greater than 0, we're in the middle of a multi-byte character. Here, the current byte must begin with 10 to be valid. If it doesn't, the input is invalid, and we return false. Otherwise, we decrement remaining_bytes by 1, and the process continues. At the end of the iteration, a final check ensures that remaining_bytes is 0. If it's not, it means an incomplete multi-byte character remains, and we return false. If all checks pass, the input is valid, and we return true. The algorithm relies heavily on bitwise operations to check the leading bits of each byte. For instance, using byte 7 and 1 allows us to extract the most significant bit efficiently. Pattern matching plays a critical role as well, ensuring bytes align with UTF-8 rules. The design includes early termination, where the algorithm stops processing as soon as it finds an invalid sequence, saving unnecessary computations. Key edge cases to handle include empty input arrays, sequences starting with continuation bytes, and incomplete multi-byte characters. The data structures used are minimal. The input array represents the bytes, and a single integer variable, remaining_bytes, tracks the expected continuation bytes. This simplicity keeps the algorithm memory efficient and easy to follow. Let's examine an example with input 197, 131, which translates to binary 11000101, 10000010, 00000001. We begin with remaining underscore bytes set to 0. The first byte, 197, has leading bits 110, indicating the start of a 2-byte character. We set remaining underscore bytes to 1. The second byte, 130, begins with 10, making it a valid continuation byte. We decrement remaining underscore bytes to 0. The third byte, 1, has a leading bit of 0, so it represents a single byte character. With all bytes processed and remaining underscore bytes equal to 0, the input is validated as a correct UTF-8 encoding, so the function returns true. Now, consider an edge case with input 235, 144, which translates to binary 11101011, 10001100, 00000100. We start with remaining underscore bytes equals 0. The first byte, 235, has leading bits 1110, indicating the start of a 3-byte character. We set remaining underscore bytes to 2. The second byte, 140, begins with 10, making it a valid continuation byte. We decrement remaining underscore bytes to 1. The third byte, 4, has a leading bit of 0, which is invalid because we were expecting another continuation byte starting with 10. This mismatch causes the function to return false, as the sequence violates UTF-8 rules. Regarding complexity, the algorithm processes each byte once, resulting in a time complexity of O(n), where n is the length of the input array. Space complexity is O(1), as only a single counter, remaining underscore bytes, is used, making the solution highly efficient. Here, we start by defining a class called solution and its method valid UTF-8, which will validate whether a given list of integers represents a valid UTF-8 encoding. The variable remaining underscore bytes is initialized to 0, and it will help us track how many additional bytes are expected for a multi-byte UTF-8 character. We then iterate through the input data, where each integer represents a single byte. To ensure we're only working with the least significant 8 bits of the number, we apply a bitwise AND operation with 0xFF. Next, we check if we are currently in the middle of processing a multi-byte character by looking at remaining underscore bytes. If it's 0, we analyze the first byte of a potential UTF-8 character. By using bitwise right shifts, we examine the leading bits to determine the character's size. For example, if the byte starts with a single 0, it's a 1-byte character, so we continue to the next byte. If the leading bits match the patterns for 2-byte, 3-byte, or 4-byte characters, we update remaining underscore bytes accordingly. However, if none of these patterns match, the byte is invalid, and we return false immediately. For non-initial bytes in a multi-byte sequence, we validate that they start with the 10-bit pattern. If they don't, the sequence is invalid, and we return false. For valid bytes, we decrement remaining underscore bytes by 1 as we process them. Finally, after processing all the bytes in the input data, we check if remaining underscore bytes is 0. If it isn't, this means we were expecting additional bytes to complete a multi-byte character, but they were missing. In such a case, the sequence would be invalid, and we return false. Otherwise, if remaining underscore bytes is 0, the entire input satisfies the UTF-8 encoding rules, and we return true. This ensures the function only validates sequences that fully conform to the UTF-8 standard. Here we have the Java implementation for validating UTF-8 encoding. We start by defining a class called solution with a method valid UTF-8 that takes an array of integers, data, as input. The first step is to initialize a variable remaining bytes to 0, which will help us track how many continuation bytes are expected for the current UTF-8 character. Then, we iterate through each number in the data array. For each number, we isolate the least significant 8 bits using number and 0xFF. This ensures we are only working with the relevant bits, as UTF-8 encoding utilizes 8 bits per byte. At this point, we check if remaining bytes is 0, meaning we're looking at the start of a new UTF-8 character. The number of bytes in a character depends on the leading bits of the current byte. If the most significant bit is 0, this represents a 1-byte character, and we simply continue to the next number. For 2-byte characters, we check if the leading bits match the pattern 110, and if so, we set remaining bytes to 1, indicating one more continuation byte is expected. Similarly, we check for 3-byte characters with the 1110 pattern and set remaining bytes to 2, and for 4-byte characters with the 11110 pattern, setting remaining bytes to 3. If none of these patterns match, the byte is invalid, and we return false immediately. Now, if remaining bytes is greater than 0, this means we are processing continuation bytes, which we'll handle next. When processing continuation bytes, the expectation is that their leading bits must follow the 10 pattern. To check this, we use the expression byte val 6 equals 0b10. If a continuation byte does not match this pattern, it violates the UTF-8 encoding rules, so we return false. Otherwise, we decrement remaining bytes by 1 to indicate that one continuation byte has been successfully processed. Once the loop ends, it's crucial to verify that all continuation bytes for the last character have been properly handled. This is done by checking if remaining bytes equals 0. If it's not 0, it means there were expected continuation bytes that were never encountered, and we return false. If everything checks out, we return true, indicating that the input array represents a valid UTF-8 sequence. This implementation ensures that every byte in the input strictly adheres to UTF-8 encoding rules while handling edge cases effectively. To begin validating the UTF-8 sequence, we start with the input 197, 131. First, we initialize the variable remaining bytes to 0, which will help us track the number of continuation bytes we are expecting. Now, we process the first byte, 197, which in binary is 11000101. Since remaining bytes is 0, we check if it's the start of a new character. By shifting the byte right by 7 bits, we see the result is 1, meaning it's not a single byte character. Next, we shift the byte right by 5 bits and find the pattern 0b110, which indicates the start of a valid 2-byte character. Based on this, we set remaining bytes to 1, as we now expect one continuation byte. Now we move to the second byte, 130, which is 1000010 in binary. Extracting the least significant 8 bits gives us the same value, 130. Since remaining bytes is 1, we check if this byte is a valid continuation byte. By shifting the byte right by 6 bits, we get 0b10, which confirms it is a valid continuation byte. We then decrease remaining bytes to 0, indicating that we are no longer expecting any additional continuation bytes. Finally, we process the third byte, 1, which is 00000001 in binary. With remaining bytes at 0, we treat this as a potential new character. Shifting the byte right by 7 bits gives 0, which shows it is a valid single byte character. At the end of the iteration, remaining bytes is 0, confirming that the sequence is valid. Therefore, the output is true. Let's analyze the second example with the input 235, 144. We start by initializing remaining bytes to 0 again. The first byte is 235, which in binary is 11101011. Since remaining bytes is 0, we check whether this is the start of a multi-byte sequence. Shifting the byte right by 7 bits results in 1, so it's not a single byte character. Shifting further by 4 bits gives 0b1110, which identifies the start of a valid 3-byte character. We then set remaining bytes to 2, as we expect 2 continuation bytes. Next, we process the second byte, 140, which is 100001100 in binary. Extracting the least significant 8 bits gives 140. Since remaining bytes is 2, we validate this as a continuation byte. Shifting the byte right by 6 bits yields 0b10, confirming it is valid. We decrease remaining bytes to 1, indicating we now expect just one more continuation byte. Now we process the third byte, 4, which is 00000100 in binary. Extracting the least significant 8 bits gives 4. Since remaining bytes is 1, we check whether this byte is a valid continuation byte. Shifting the byte right by 6 bits results in 0b00, which makes it invalid as a continuation byte must start with 0b10. Because of this invalid continuation byte, we immediately return false. The sequence is deemed invalid, and the output is false. In this final example, we consider an edge case where the input is an empty list. As usual, we start by initializing remaining underscore bytes to 0. Since there are no bytes to process, we directly check the value of remaining underscore bytes. With remaining underscore bytes still being 0, we conclude that the sequence is valid. This is because an empty input does not violate any UTF-8 rules. Therefore, the output for this case is true. The time complexity of our solution is O(n), where n represents the length of the input array data. This is because the algorithm processes each element of the array exactly once. To break it down, the outer loop iterates through every byte in the array, and since there are n elements, the loop runs n iterations. Within each iteration, the algorithm performs several constant time operations, such as extracting the least significant 8 bits with number and 0xFF, performing bitwise shifts like byte 7, and making comparisons. These operations are all O(1). Additionally, decrementing the remaining underscore bytes counter and verifying conditions are also constant time. When we combine these O(1) operations with the n iterations of the loop, the total time complexity becomes O(n). Now let's look at the space complexity, which is O(1). This is because the algorithm uses only a small, fixed number of variables regardless of the size of the input array. Specifically, it relies on variables like remaining underscore bytes to track how many bytes are left to validate and byte to store the current processed 8-bit value of each byte. Importantly, it does not use any additional data structures such as arrays, stacks, or hash maps. Instead, the algorithm operates directly on the input data, ensuring that memory usage remains constant. Since no extra memory is allocated that scales with the size of the input, the space complexity is O(1). To better understand the efficiency of this solution, let's compare it to a naive approach. A naive method might involve converting each number in the array into its binary string representation and analyzing it. While this approach could work, it would significantly increase both time and space complexity. For example, converting a single number into a binary string requires k time, where k is the number of bits, which is 8 in this case. For an array of size n, this would result in a time complexity of n*k, which simplifies to O(n), since k is constant. However, the space complexity of such a solution would also be O(n*k), as we would need to store these binary strings. In contrast, our solution avoids these overheads by performing in-place checks without creating new data structures, achieving optimal O(n) time and O(1) space complexity. Finally, let's analyze the algorithm's performance in different cases. In the best case, where all the bytes represent 1-byte characters like ASCII, the algorithm still processes each byte in the array, resulting in O(n) time complexity. In the average case, where the input contains a mix of 1-byte and multi-byte characters, the algorithm continues to process each byte individually in O(1) time, maintaining an overall complexity of O(n). Even in the worst case, where every character is a 4-byte UTF-8 character, the algorithm remains efficient. Since it processes each byte exactly once, the time complexity does not change, it stays O(n). The space complexity remains O(1) across all cases because the algorithm does not use additional memory that scales with the input size. This consistent performance demonstrates the algorithm's asymptotic efficiency, making it an optimal solution for validating UTF-8 encoding. When working with UTF-8 validation, there are several common mistakes to be aware of. First, not understanding the UTF-8 byte structure can lead to errors. Each multi-byte character is defined by specific bit patterns. For instance, a 2-byte character must begin with a byte starting with 110, followed by additional bytes that start with 10. Misinterpreting these patterns results in failing to validate the encoding correctly. Another frequent mistake involves incorrect use of bitwise operations. For example, confusing the bitwise an operator and with or applying the wrong bit mask, such as using 0b11111100 instead of 0b11110000. These errors lead to logical flaws during the extraction or validation of bits. Additionally, not checking the input length early enough can cause issues. If a multi-byte character starts, but there aren't enough bytes left to complete it, the validation must fail. Ignoring this can result in index errors or invalid results. Finally, skipping edge cases like empty inputs, single byte characters such as ASCII, or the maximum valid 4-byte representation can leave your solution incomplete or produce incorrect outcomes. Inefficient iteration is another common pitfall. If you're rechecking bits for every byte instead of processing groups of bytes together, you're wasting valuable computation time. For example, repeatedly validating the leading byte of a character instead of skipping over valid sequences can cause unnecessary slowdowns. When it comes to interviews, there are a few key insights to keep in mind. First, pattern recognition of the leading bits in UTF-8 encoding is essential. For example, recognizing that a byte starting with 0 represents a 1-byte character, while 110 indicates a 2-byte character, is fundamental. Mastery of bitwise operations, such as masking with and shifting with, is also crucial, as many interview problems test your ability to manipulate bits accurately. Additionally, being prepared to discuss how your solution handles edge cases is important. This includes invalid inputs, sequences exceeding the 4-byte limit, or random invalid byte patterns. Lastly, be ready to talk about optimization. Understanding the trade-offs between single-pass and multi-pass solutions, and emphasizing the importance of linear time complexity for processing large inputs, will demonstrate your ability to think critically about performance. To deepen your understanding of UTF-8 validation, it's useful to explore related problems that reinforce similar concepts. For example, LeetCode problem 190, reverse bits, focuses on bit manipulation, a skill that's highly relevant when working with UTF-8 encoding. Another example is LeetCode problem 136, single number, which centers around XOR operations, a fundamental technique in many bitwise problems. LeetCode problem 201, bitwise and of numbers range, is another valuable exercise that tests your ability to apply bitwise operators effectively. Lastly, LeetCode problem 268, missing number, shares logical similarities in iterating through sequences efficiently. These problems are excellent practice to build fluency with the techniques required for UTF-8 validation and related challenges. There are also alternative approaches to solving UTF-8 validation problems, each with its own trade-offs. One common method is direct bitwise validation, where you use masks and shifts to check each byte in sequence. This approach is efficient, with a time complexity of O(n), but it requires careful attention to edge cases and accurate application of bitwise operations, as mistakes can easily occur. Another approach is table-driven validation, where you pre-compute valid byte patterns and use them for lookup. This avoids repetitive bitwise calculations and can improve runtime performance, but it comes at the cost of higher memory usage. A less conventional option is regex-based matching, where you represent UTF-8 byte patterns as regular expressions. This simplifies the coding process but is generally slower in performance. Finally, iterative parsing involves processing the input in chunks based on the leading byte, validating each group as you go. This method is intuitive and easier to follow, but it may be slightly more complex to implement compared to a single-pass solution. Each of these approaches has its strengths, so the best choice depends on the specific context and constraints of the problem. Great job! In this session, we solved LeetCode problem number 393, focusing on UTF-8 validation using bit manipulation. We discussed the algorithm's time and space complexity and highlighted key takeaways, such as the importance of understanding encoding rules and binary operations. Thank you for watching, and I hope you found this helpful. Don't forget to subscribe and keep practicing to excel in coding interviews. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!